Okay.
Let me share.
Yep. Thanks.
All right. It's Dr. Beltmead, right?
Yeah.
I want to make sure I address you correctly because I'm anticipating a question from you. So, good afternoon, everybody. My name is Caleb Bruto. I am an undergraduate researcher at the University of Houston. My research advisor is Dr. Gamanu Gunaratna of the physics department at UH. And today I will be discussing a technique to move closer to ideal filtering in a demonstration using compact binary merger data from LIGO. So to summarize what I'll be discussing today, I first want to give a little bit of a brief detail on LIGO astronomy instruments, the noise that they're subjected to, as well as the nature of the astrophysical signals that the instruments observe. I'll then talk about the signal processing pipeline known as CBC analysis that uses a technique called match filtering and inclusively Welch's method to locate where a candidate signal is in real space. This will lead me to go over what Welch's method is, as well as the adjustments that we made to Welch's method and then the resulting improvements. So aLIGO, or Advanced Laser Interferometer Gravitational Wave Observer, represents a dual network of interferometers, one located in Livingston, Louisiana, and then one located in Hanford, Washington. And then to briefly explain how the interferometers work, the instrument splits the laser beam into perpendicular directions. And then these laser beams go out about 4 kilometers. They bounce off of mirrors, they come back, and then they're superimposed to create a wave interference pattern that quantifies the stretching and contraction of space-time of a gravitational signal. The signal is characterized by an astrophysical source of compact binary objects, such as neutron stars or black holes, in a 3-phase fashion. First is the end spiral, in which these compact binary objects spiral each other, creating a rotational a rotating gravitational quadrupole moment that harmonically perturbs space-time. And then there's the merger, and then there's the ring down, where the now singular object essentially oscillates in a decaying fashion. This produces a waveform characterized by a chirp signal that we can see. I don't know if you can see mine. Okay, yeah, you can see my mouse. It's characterized by a chirp signal from numerical relativity. So when the astrophysical signal reaches Earth, it's incredibly weak, on the order of less than 10 to the negative 18 meters in magnitude. So the instruments have to be exceptionally sensitive, and the LIGO scientific collaboration has done an incredible job of this. However, there's several artifacts of noise that are present around the instruments. So additional signal processing is required to find the signal embedded within the noise. So CBC, which is a signal processing pipeline written in Python, identifies candidate signals by computing a signal to noise ratio given by this equation right here, where S represents the signal strain, and then H represents the template waveform produced via numerical relativity. And then we can see here the inner product is taken to cross-correlate the template with the strain, and then the noise characterized by the power spectrum then divides out. The noise is divided out with the estimated power spectrum to reveal this plot where you have the SNR as a function of time. And then you can see there's a peak right here. And the people at LIGO can now use this graph to identify where exactly in real space this signal occurred. And then they can do their signal consistency and significance analysis in order to determine the confidence level of this candidate event. Okay, and then the SN as a function of frequency right here, that's the part that we want to focus on. Is there a different method that can be used to estimate the noise even better? Because if you can divide more noise out, you can get a higher SNR peak. So let's look first at what PyCBC does. PyCBC uses a very standard approach. It estimates the power spectral density of the noise using Welch's method. This is where you need the noise in frequency space, but the strain itself is non-periodic. So you have to divide the strain into several segments with the exception of the middle segment, because that's where the signal can potentially be embedded in. You take each of these segments and you multiply it by this very simple function, the sine squared function that tapers the signal at the end of each segment. And then you put each segment right here in frequency space, and then you take the median or average values of all these segments to get the estimated PSD, which you can later use in this match filtering calculation to divide out the noise. And it does a pretty good job of it. However, we wanted to ask ourselves and explore what the consequence would be if one were to exchange the Hann window with a different window. And it's always true that in nature, if you want to get something, you always have to give something up. And in the case of windowing, in the case of windowing, the compromise is between keeping information and being able to periodize the signal. So the question we wanted to answer is, what is the optimal balance between these qualities? And ideally, you can use a square window to keep as much information as you can, but you're not periodizing the signal. So the result is, if you try to put it in frequency space, you'll get what's called spectral leakage or excessive pinging. So this is where we introduce what's called the kDAF, or the K-domain distributed approximating functional. And I don't have enough time to get too much into the detail of it, but it's important to note that the function uses two parameters. One is the signal right here, which is the standard deviation of the Gaussian. And then the other is this n/2, which is the truncation of the sum. And you can use these two parameters to essentially tune the window and adjust it to get a certain SNR. And in this case, this is exactly what we did. So the truncation of the sum will determine the width of this flat top of the window right here, while the sigma itself will determine how steep this roll-off is. Thank you. Essentially, using the bisection method, looking at these two parameters, we tried to find, what's the highest SNR that this window could produce, and this was the result. So these are 5 events from the first observing run, which was from 2015 to 2017. These right here are the values of the SNR for the data for the Hanford detector. And then these are the values that we calculated for the Livingston detector, labeled L1 and H1 respectively. Now SNR is a power quantity. So in order to get the network SNR, the overall SNR, you have to take the quadrature sum, which is simple. It's just this value, this quantity squared plus this quantity squared, square root of that. And then we compared it to the original SNR that you would get from using the Hann window. And you can see, sorry, this is obscuring it, but the average network SNR improvement was about 4.82%. So in conclusion, the incoming signals from binary black holes or binary neutron stars are extremely weak signals, on the order of 10 to the -18, and even less than that. So, and there's noise artifacts that are present with the interferometers. So it requires extra signal processing to divide out as much noise as you can from these anthropogenic sources from human activity in order to find the actual signal embedded in the noise. So the only adjustment that we made to PyCBC analysis is replacing the Hann window with the kDAF window in Welch's method. And then we looked at five events from the first observation run, and we noticed a 4.8% improvement, which seems small, but in the context of the sensitivity of the measurement, we believe that this is a potentially significant improvement in one's ability to observe and confirm these astrophysical events. But obviously more research needs to be done to corroborate this claim. So I think that's the end. Before I take any questions, I just wanted to acknowledge once again my mentor, Dr. Gunaratne, as well as a previous mentor of mine, the late Dr. Donald Khoury, who alongside Dr. Gunaratne, Dr. Dave Hoffman, and other contributors developed the distributed approximating functionals that we used in this research. He was a previous mentor of mine for 8 months until he passed away earlier this year. And he takes a lot of credit for motivating me to pursue science at a much higher level than I already was. So thank you. Yes, Dr. Hill.
After you challenged me, I'm going to give you a question. So this is very interesting. So clearly this is a high sensitivity measurement, but it has a relatively good signal to noise ratio to start off with.
Yes, yes.
And I'm just wondering if you look at the frequency change as a function of when you go from in spiral back into the merger, and then you look at the amplitude, where is really the improvement? Or what would change in this spectrum?
So let me reiterate. So this model right here that's a template created from numerical relativity. So essentially, like what's happening is in this cross correlation calculation, they're taking this template and then they're cross correlating it with the strain itself to try to find a peak. So in all frequencies, essentially, within the certain frequency band of the astrophysical signal, which is within, I want to say 30 hertz to 400 hertz. Don't quote me on that, but it's around that frequency band. But yeah, that's essentially what's happening.
So in that frequency band, your signal to noise improvement is constant.
Yes, yes, absolutely. So the SNR is within. So signal to noise is the signal to noise ratio is given in real space. It's not given in the frequency. Not given in the frequency domain. So when you have the plot of the SNR and you see a peak, it's at a certain time. So it's not in terms of frequency. So I don't know if that answers your question.
I'm not sure whether it answers.
Yeah, I work on LIGO stuff too, and it's really good. They're nice talk. So okay, so I think again, correct me if I'm wrong. You're not really subtracting noise off of the strain. You're trying to estimate. So there's that denominator, that Sn of f, and that is a function of frequency. That the denominator of your integral over there.
Yes, but yeah, ultimately.
Yeah, and so people are trying to estimate. You know, you can't predict that a priori. It'd be wonderful if you could. So basically, by looking at chunks of the data that are thought not to have signals in them, you're trying to empirically determine that thing.
Absolutely.
And your function, your approach is just, again, there's this trade-off, like you said, between leakage and throwing out data, and you're trying to optimize that in some way. And so I think what Renee's question was is when you're saying you're raising the signal to noise, what you're really you're not changing the signal, obviously, and you're not really removing noise from your detector.
Giving a better estimate.
Yeah, you're saying that other people are overestimating the noise, and so if you have a lower estimate of the noise, then obviously if the denominator goes down, that's
I
noise
wouldn't
goes
say
down.
a lower estimate, but perhaps a more accurate estimate of the noise around a particular event. So you can calculate the general noise, but this Sn of f, every time they make an observation, they have to recalculate.
Redetermine. Okay, so I guess the question is, following up Renee's question, where in the, at what frequencies are you getting an improvement in that function? And also my second question is, how did you optimize this? You're trading off the thickness, the width of the peak and the sharpness of that thing. How did you optimize it?
So when it comes to the power spectral density calculation, you can see sort of the frequency band here, and this is within the limits of LIGO. But you can see it's around, they initially use a high pass filter to filter out the noise from low frequency artifacts, because that's no astrophysical signals are going to be within that frequency. But you can see just approximately it's within the frequency band is within 10 to just above 2000 or so hertz. But the actual signal itself, because you can notice that this frequency plot here, the PSD as a function of frequency is non-uniform. It's varying, and it's only right here around this region where they can actually make the actual astrophysical observation. So, and anything higher, we don't worry about it. That all gets filtered away. So I hope that answers your
So
question.
how did you I guess your N, how did you choose N and sigma to optimize your window?
So the segments, we divided the strain into 8 segments, and then let's see, so the frequency bends, it's 32 seconds of data. So, and then it's at 2048 hertz. So, and then if you divide, I think it's like 16K points of data, you divide that into 8 segments. So I don't know the exact number, but it's from 0 to N of each segment. So I'm going to guess that's 32 divided by 8, that's 4. So that's 4 seconds times 2048 hertz. So that's about 8,000 or so points of data. So 0 to N is 0 to 8,000.
Okay. I don't know if people want to ask questions.
Okay. Any more questions? Okay, thank you.
Next we have, will the black hole still collapse by Hann?